Everyone, my name is Adarsh Kumar. I am a final year dual degree student in the Department of Chemical Engineering at IIT Kharagpur. So today the topic I have chosen for the discussion is second law of thermodynamics. So before moving on to that into second law of thermodynamics, we need to understand what is the first law. So let me give a brief of first law of thermodynamics. So basically it states that energy will always be conserved. So with this in mind, let's take an example of a hot cup of tea that is at 45 degrees Celsius and the surrounding it is 25 degrees Celsius. So here comes a concept of system and surrounding. So let's understand what is system and surrounding. The process that we are going to study or going to uh, have our study on this, that is we define it as system, and anything that is except system is surrounding. So here we generally with our intuition say that energy is getting transferred from hot body to cold surrounding. But according to first law, either case is also possible, that energy is getting transferred from 25 degrees Celsius to 45 degrees Celsius. That is from lower lower surrounding to hotter higher to higher temperature. But with our intuition we can say it is not the case. So here comes the limitations of first law. First is it does not tell about the direction of the flow. So let's take another example of a jar where two gases A and B are taken. So if these A and B will get have a chemical reaction between them is possible or not, we cannot say. So uh, we there comes a second law, second limitation, that is it does not, first law does not tell about the feasibility of any process. So to overcome these limitations we introduce a law, that is second law of thermodynamics. So let's move on to what it states. So talking about the second law, it states that the entropy of universe of an isolated system will always be greater or equals to 0. So here we have introduced a new word, that is entropy. So what we mean by entropy? So let's take an example to understand this. So let's take example of a chamber where two gases are taken. One is A and another one is B. And here you can see there is a partition in between them. So if we take a element, a molecule from left side of the container, it will be A. If we take a molecule from right side of the, it will be B. But after removing the partition, if we these molecules will get diffused into each other, and we cannot, if we take a molecule, we cannot say it is A or B. We can also see there is an increased randomness. So to account for this randomness, or to measure the degree of randomness, we introduce a new state function, that is entropy. Basically this entropy is combination of two things. First is internal irreversibility, and another one is external interaction. So we can write it as ds for entropy equals to s dot g for internal irreversibility, and plus dq upon dt for external interaction. So let's take two processes. First is reversible process. For this we can say S dot G, that is the term that due to internal irreversibility will be 0. So we can write ds will be equals to dq upon t. So moving on to another type of process, that will be adiabatic and reversible. So for this we can say S dot G term equals to 0, and another term, that is dq, that is external interaction, will also be 0. So our entropy change will become 0. So for this we have also say this is a isentropic process where entropy remains constant. So with this background of entropy, let's move back to the second law of thermodynamics, that is delta S inverse will always greater than or equals to 0. So let's look into the example that we have earlier taken. A cup of hot tea with at 45 degrees Celsius and surrounding at 25 degrees Celsius. So let's talk about two cases. Uh, First case, let's take against our intuition, that is energy will be transferred from lower temperature to higher temperature, that is from surrounding to hot cup of tea. Let's say it is 10 joule. If we write delta S, so for system it will be plus 10 upon 45 degrees Celsius, that is 45, plus minus 10 upon 25. Here we can see delta S is coming out to be negative. We'll take another case that 10 joule is getting transferred from hot body to lower body to surrounding at lower temperature. So for that we will write delta S equals to, for system it will be minus 10 upon 45, plus for surrounding it will be plus 10 for divided by 25. It is coming delta S will be greater than 0, that it is positive. And we will say this is the case of our intuition, and it is also stated in the law. So this is not possible. So based on the second law of thermodynamics, two statements are proposed. So we'll look into that one by one. So first a statement is Kelvin Planck's statement. So we will try to learn it in simple languages, that if we try to convert Q, that is energy, into work with the help of heat engine, so it is not, some energy will be lost in the surrounding, that the whole energy will not be converted into work. So this is the Kelvin Planck's statement. So let's move into another statement, that is Clausius statement. So it is said that a body at lower temperature, the energy from a body at lower temperature cannot be transferred to a body with higher level of temperature. So for this we need a external help to do this. So what is this external help, external work, or external thing to do this? So sorry, there is a correction. It is not Ca, it is Cl. Okay. So to transfer heat from lower temperature to higher temperature, we need an external help. So here comes the application part, that is refrigerator, where V, where the energy from lower body is transferred to higher a higher temperature, taken from surrounding, that heat taken from surrounding to a lower, sorry, from a colder one to hotter one. So these, so basically we have talked about limitations of first law, what is second law of thermodynamics. We have also talked about entropy. We have also proved we have also seen how the statement of second law is valid with a real life example, and we have also studied two statements that is proposed based on the second law of thermodynamics, and finally we have also looked into the application part. So that's all from my side. Hope we will meet again.